In the standard called data, we're going to be analyzing that data. That means taking the raw numbers and manipulating them in some way to give a conclusive answer or to reduce a large set of trials, large set of numbers, into one meaningful number. So the very first learning objective is I can apply appropriate arithmetic analysis methods, e.g., and e.g. means examples essentially, means, modes, medians, sums, percent error, etc. Basically, if you are applying some kind of arithmetic to your raw data, that's what I'm talking about. The most common, of course, is going to be a mean, an average. But then, of course, a percent error is important as well. Let's take a look at a blank spreadsheet. So this is the spreadsheet we're going to put in our data for our pendulum experiment. And you notice I've already filled in that we have the length in meters. So that's what that means with the parentheses. It means that everything below this is going to be in meters. Generally, when you're working with this spreadsheet software, you should not put units in the cells that hold the numbers, because this software knows how to treat numbers. It can do math with them, and it can take averages, it can multiply, it can divide, but it doesn't know how to do multiplication, division, and all that for things that are not numbers, so for letters. So leave the letters out of it. Leave the units up at the top in the parentheses. So we started the experiment with 0.2 meters. Another thing we need to do is represent how precise our measurements were. So this wasn't just 0.2 meters, but really we had a bit more precision. So we can use these two buttons up here, increase and decrease decimal places, to increase the decimal place at least one more. I would say this is about the level we have, precision we had, to the nearest centimeter, essentially. The total time for the first trial, which was at 0.20 seconds, was 8.43 seconds. So that was, again, for the full 10 cycles. And the period is going to be the total time divided by the amount. And this is an example of taking an average, actually. We're taking a mean here. We're taking a total time that was added up. You can think of it as each swing of the pendulum, we added the time together and then divided by the number of swings. That's an average. That's an arithmetic mean. So if we go back here, we can see that we are applying a mean to this. So this is relevant to this learning objective here. So instead of breaking out our calculators and calculating it in, I would always recommend get familiar with putting in equations into the spreadsheet software itself. And this is how you do that. Hit the equal sign. And what the equal sign says to the computer is, hey, the following is going to be an equation. And what you can do is you can click on cells. And notice it says B6, B4, C4, D3. This is basically like battleships, if you ever play the game, board game Battleships. We have columns. These columns are letters. And we have rows, and the rows are numbers. So if you have a combination of a letter and a number, you have a specific cell in this spreadsheet. So we're going to click on the total time spreadsheet. And if we just hit enter right now, all it's going to do is going to take whatever the value is here and put it in over here, which is nice because if this ever changed for some reason, it would update the right one as well. But we don't want to change it. So let's go back into that cell. We're not done yet. We want to take that number and divide it by 10. So we're just going to hit that slash symbol, that means division, and type in 10. Hit enter. That's going to get us our period for one oscillation. And now we're going to do the same thing for filling out the data table for all the trials that we did. Little tip, we could put that the next one was going to be 0.4. Also, we want to apply the same formatting we had before. So what you want to do is click on the cell you like the formatting of, and you click on this paint format button, and then you can click and drag down, and now it's going to apply the same formatting that you did for one cell. So what you could do is you can make one cell just the way you want. Maybe you want to change the font, maybe you want to change the color, and then you click on that cell that you like, and you click on the paint format, and you copy or select all the cells that you want to apply that to. We can do the same thing here. A good title for a data table probably would make bold. Yeah, make the titles of the columns bold. And I like putting them in the center too. So if I wanted to apply this to the rest of the column headings, so I can hit paint formats when I'm clicking on the one that I like and apply it to the rest over here. And now you can see they look much more like actual headings to a table. So we have 0.4, and we could type in 0.6 and 0.8, but instead of doing that, let's highlight the first two here, 0.2 and 0.4. The computer should recognize that we are increasing by 0.2. So if I click and drag, so if I go to where on the bottom right corner of the cells, there is a little circle and my cursor turns into a crosshair. If I click that, hold it and drag down, it's going to apply that difference all the way down. This, for like 5 trials, this is not really that important, but what if you had 100 data samples? This is incredibly time saving. All right, let's fill in the rest of the data. Now, the same thing with the whole click and drag trick that I showed you before can be applied to equations. So right now, this equation is taking essentially whatever the cell is to its left and divide by 10. So if we click and drag on the bottom right corner down, it's going to do the same thing. Each row is going to apply whatever's to the left of it and divide by 10. So you notice we did not have to retype in that equation each and every time. This saves us lots of time. I'm just going to shrink up some of the columns to make them a little bit narrower. And there we go. We have now found the arithmetic mean for each of the times, for each of the different lengths. The next learning objective we need to talk about is data point 2, which is I can graph sets of data and apply lines of best fit. This is a really valuable skill for science. We need to see if there's a correlation between the total time and the length. Now we can clearly see that as length increases, so does total time, but in what way does it increase? Well, here we can plot this data. What we're going to do is we're going to highlight these two columns, and what we can do to do that is hold Control down and click on the columns, and that's going to be able to highlight both of them at the same time. And what we can also do is hit Insert, Chart. Now it's going to put a chart in here, and I'm going to have to zoom out a little bit to see it all. Okay, so here's our chart with the period versus length, and notice it gave it an automatic title because I've titled my columns. And also look, it also gave the titles for the axes because, again, I've titled my columns. So if you title your columns in your spreadsheet, it will automatically apply headings for both the overall chart and also for the individual axes. And it has plotted the points. Most of the time in science, we want this kind of plot right here. We want what is called a scatter plot or scatter chart. If it's not in a scatter chart format, you can click under Setup, Chart Type, and click the one you like. It could be a line here, but we don't want that actually, because line here implies that we have a continuous data points. We don't. We have discrete data points here. Or lots of other things. It doesn't really make sense for it to be a pie chart, but it could be a pie chart. And it would automatically reformat it. This learning objective says I can graph sets of data and apply lines of best fit. So we need to be able to apply a line of best fit to this. So we're going to go to Series. Series means essentially our data points. Not sure why they call it series. And we're going to add in on the very bottom here, scroll down, trend line. You're going to click on trend line, and it's going to try to apply a trend line to that. Now, our original hypothesis was that period is going to increase by the square root of length. So the graph that we should see shouldn't be a perfect line. And if you actually look at this, it doesn't look like one. In fact, it starts lower, goes higher, and then ends up a little bit lower. So it has a bit more of a curve to it. So a linear fit wouldn't quite make sense, for at least for this data. We're going to do something called linearization in a moment. But we could apply other types of fits to this. Like, for example, we could apply exponential. That doesn't make sense. It looks even worse, actually. What about polynomial? Oh, that's pretty good, actually. Now, using polynomial, especially to a lot of degrees or changing that, is not recommended because it's kind of like cheating. You're going to get a good graph almost no matter what. So it's not the preferred method. And there's also logarithmic and power series. Power series would probably be closer to what we're working with. It'd be nice if it showed us the equation as well. Under label, instead of using none, we can click use equation. So now it's using the equation. It's showing us what equation it used to plot that line on there. And if you look, this says x to the 0.534. 0.5, x to the 0.5. What is something raised to the half power? That's a square root. So it seemed to think that a good fit to this would be if we took the square root of our x values, which is length. And that's our hypothesis. But we're going to do this a better way. We're going to do this a better method. I'm going to delete that graph. And instead, what we're going to do is we're going to add in a column here. So I'm going to right click on the B column, and it says insert one column to the left. I'm going to go ahead and do that. And I'm going to label this square root length. Now notice that doesn't quite fit. So one thing we can also do is highlight all the columns, and let's change it to wrap the text. That's going to make it just take up more vertical spacing. And this is going to be in units of, well, it's going to be in units of meters per 1/2 power. Because if we took the square root of a meter, it's a meter raised to the 1/2 power. Weird units, I know. All right, let's apply the equation where we're going to take the square root of the length. Because our hypothesis is that the square root of the length is going to equal, or be proportional, I should say, to the period. We're going to click right there, hit equal sign, and then we're going to type in the word square root. Actually, SQRT is the acronym for the square root in this. So it's going to take the square root of a value. If you ever want hints or help with these equations, you can start typing something in and it tells you like, hey, here's an example of how to use square root. You SQRT and 9, and it returns the positive square root of a positive number. Really helpful. So we're going to click on, we're going to make sure it's in there, and we're going to click on the column to our left, just the cell. Close the parentheses, but if you don't close the parentheses, it will probably do it for you automatically. Hit equals, and guess what? It's suggesting that we apply the same thing going down. So we're just going to hit yes. Let's go ahead and apply the same thing going down. Now this is too many digits. So we need to decrease the amount of decimal points until it's more appropriate. Now we only had 2 sig figs of precision here, so we should probably only have 2 sig figs of precision there, although we had 1 for 1. Now what I'm going to do is I'm going to plot these two, and let's see what we get. All right, now we've plotted the period versus the square root of the length. So period again in the y, and square root length in the x-axis. This looks a bit more like a line, a linear graph. Well, let's check it though. We can go to series again, go down to trend line and apply a trend line. That's a pretty good trend line. And we can apply the equation. So here's the equation right there. We have 2.08 times x, remember x is our length, plus a negative 0.067. If we remember from algebra, this equation is following the format of mx plus b. So this value right here, there we go, highlighted it, is the b, it's the y-intercept, and this value right here is essentially the slope. Now, that looks like a good line to us, but we need to be able to verify that it's a good line using some kind of number. That's where we're going to apply this little button here that says show r squared. The r squared value is essentially a number that indicates how good of a fit is this line. How close is this line to all the data points? And right now it's reading that it's 0.998. What does that mean? Well, a perfect fit, meaning all your data points are exactly on the line, has a value of 1. If you had something for, let's say, that is not a perfect fit, so something that is seems to have no relationship between the two values. It's going up, down, up, down, up, down. It's going crazy. There's no obvious trend upwards. You know, as square root length increases, the period doesn't seemingly increase. This r squared value would be close to 0. So the closer it is to 1, the better your data fits that model. The better the data fits that line that you applied. So this trick that we did, where we took a length, took a value, and did something to it before plotting it, is called linearization. We figured that we probably would need to take the square root of it. And once we took the square root of it, then we would have a line. And once we have a line, we can imply correlation between these two values. There is a correlation between the square root of the length and the period, and it is a linear correlation. That would cover data point 2, which is I can graph sets of data and apply lines of best fit where relevant. Now, data point 3 is about constructing well-formatted data tables. So that was all the tool tricks that I showed you when setting up this data table. Making sure there's no numbers in here, making the titles look like titles, and applying equations in your spreadsheet. All of that is testing that learning objective right there. And data point 4 is specific to spreadsheet software because all of this could have been done by hand on a piece of paper. But using spreadsheet software to automate and simplify mathematics is a very valuable skill. In fact, I would go so far as to say it's probably one of the most valuable skills you will get from this class, because that can be used in almost any career. Almost every job uses in some way this spreadsheet software, especially for any businesses. Definitely use this in tracking expenses, for example. So that covers the entire standard of data. How do you analyze data? How do you graph data? How do you use spreadsheet software to analyze your data? The next step after we have this data would be going into reasoning.